Hello, I'm going to be doing a transport homework problem for you guys today. A 10 centimeter long uniform cross-section capillary initially contains pure liquid H2O and D2O on its left and right halves respectively. At t equals 0.1 seconds, the maximum molar diffusion flux was 2.78 moles per meter squared per second. D2O molecular weight and density are 20 grams per mole and 1,110 kilograms per meter cubed. What is the overall mass flux corresponding to the maximum molar diffusion flux? And they give us a hint. They say the maximum diffusion flux occurs and consider where it occurs and calculate the concentration of H2O at that location. So the first thing I like to do before I approach any problems, I like to draw a picture. So I drew a picture. On the left, I have H2O, and on the right, I have its deuterium. And it's goes from 0 to 10. It's split in half, so both sides are equal. So we have a sense of what we're looking at. Now, we need to calculate the total mass flux. But we know the formula of it. The total mass flux is equal to the mass concentration times its mass average velocity. Now, this is important. They said, calculate the concentration of H2O. So we know that we need to calculate the concentration. So the total concentration is equal to the sum of the two components. It's a binary system. So the mass concentration of H2O plus the mass concentration of D2O is equal to the total mass concentration. So the mass concentration of the individual component is equal to the mass component of I over the total volume. And that is also equal to the density multiplied by its individual velocity divided by its total volume. And we also know the total volume is equal to the sum of the two components, H2O and D2O. So now that we have the equation for the total mass concentration, we must find the concentration of each individual component. So now we're going to find the mass concentration of H2O. So we plug in the numbers, and we see that the total volume cancels out, and we are left with 500 kilograms per meters cubed. And we do that for D2O as well. We plug in its density and its individual volume over the total volume, and we get 555 kilograms per meter cubed. And the sum of those two components is equal to the total mass concentration. So, as you can see, we add up the two components, and it is equal to 1055 kilograms per meter cubed. So that's perfect. We found the first part of the problem, 1055 kilograms per meters cubed. Over here, we found this. But now we need to find the mass average velocity. And how are we going to do that? We do know that the maximum molar diffusion flux was 2.78 moles per meter moles per meters per second, meters squared per second. I'm sorry. Okay. And we also know that we're going to claim a direction. We're going to say it's going in the positive Z direction. It's going in this direction. And since I said it's going in that direction, that means H2O is positive. D2O is going in the negative direction. We know that the sum of the total molar diffusive flux is equal to the individual components. It's a binary system that has two components. We know that the molar diffusive flux is equal to 0. When it's fully diffused, it becomes 0. And since we know it's 0, we know that the diffusive flux, the molar diffusive flux, is equal to 2.78, and the molar diffusive flux of D2O is negative 2.78. Now this is important. This is going in the negative direction. This is in the positive direction. So, what can we do to figure out the mass average velocity? Well, we can use an equation that we know. The molar diffusive flux is equal to the molar concentration times the velocity of the component. And that molar concentration, we can break that down even further and say the molar concentration is equal to the moles over the total volume. And we can also say that the moles of the component is equal to the mass of component I over the molecular weight of I. We do know that we plug this into here and we plug this into here and we're left with this equation. We know the mass of component I, that is also equal to the density multiplied by its individual volume. And we're trying to solve for the velocity of the component I. So, specifically the velocity of H2O and D2O. So we plug everything into the equation and we solve for the velocity of H2O, and we are left with 1.0008 times 10 to the negative 4 meters per second. And we do the same thing with its deuterated form, and we find it to be negative 1.0018 times 10 to the negative 4th meter per second. So now we have the velocity of both components. Now we need to find the mass average velocity of both components. So how are we going to do that? So the velocity is equal to the mass fraction multiplied by the volume, multiplied by the velocity of water, plus the mass fraction of D2O multiplied by the velocity of D2O. But there's something that we don't know. We don't know the mass fraction of water or D2O. But here's the thing. We know that the mass fraction is equal to the mass concentration over the total mass concentration, and we have both of those. We solved for both of them. So we're gonna plug this into the equation for its respective variables, H2O and D2O, and from there we're able to plug in all the values that we got above and get the velocity, the mass average velocity of the system. It's perfect. We found the mass concentration, total mass concentration of the system, and we found the mass average velocity. We plug that in and we get the total mass flux, which is negative 5.56 times 10 to the negative 6. Now for problem number 2. They're asking, make an order of magnitude estimate for the maximum driving force for diffusion at t equals 0.1 seconds. So we know the sum of the molar diffusive flux is equal to 0, that we figured out above. So we know that J2 is equal to negative J1. We know the total mass fraction is equal to 1. So x1 plus x2 is equal to 1. And if we isolate x2, we get 1 minus x1. Now we have the equation for the driving force, and that is equal to the derivative of x with respect to z. From I to n, the mass fraction multiplied by the diffusive flux minus the mass fraction of that component multiplied by the diffusive flux divided by the molar concentration multiplied by the Stefan-Maxwell diffusivity. Now, we have two components of this system, which means we're going to go through two iterations. Now, when we go through two iterations, we find that the first terms cancel out and this goes to 0. So we're only left with this. And from here, we realize that we can't really solve it. We have x1, x2, j2, j1, but hey, remember, we said j2 is negative j1, and we said x2 is 1 minus x1. Now we plug that in and solve for the equation, and we get the driving force is equal to the molar diffusive flux over the molar concentration multiplied by the Maxwell diffusivity. Now, we know we plug in all the values. We have this value. We already have it above. We got this value from the first equation from above. And we also have 10 to the minus ninth, which is the Maxwell diffusivity. So how do we know that it's 10 to the minus ninth? Well, this is an experiment number. There's been many experiments. They found it. And this is for liquids especially. For solids, it's a different number. For gases, it's a different number. But for liquids, it's 10 to the minus ninth. And then we finally get negative 5.007 times 10 to the fourth. And we find that the driving force is 10 to the fourth. Now, the third part of the problem asks us to sketch the initial, intermediate, and final mass transport profiles. Okay. So we're going to do that right now. And they said label the equation, label the x-axis and the y-axis, and we're going to find it. So we're going to scroll down. So the initial, they said, it was at t equals 0.1 seconds. Intermediate was t equals 60 seconds. And then at final was t equals infinity. Now, the first was the mass concentration. We can see on the left and the right, we have H2O on the left, and at the right, we have its deuterium. You can see it's at like about 1100. And you can see that nothing is really happening right now. It's at 0.01 seconds. It hasn't really crossed any boundaries. But at t equals 60 seconds, you can see that it's starting to combine together, go into their respective origins in their area. And you can see at infinity it reaches equilibrium. The H2O and D2O fully mixed together, and their D2O is on one side, the H2O is on one side, and they're mixed together. Now, it's molar concentration. The same thing is happening. At 0.1 seconds, we're not really seeing anything. At its left and its right, we can see that it's pretty steady. Nothing's really happening. But at t equals 60 seconds, you can see that it's starting to diffuse together, and it's starting to slowly diffuse together. And at t equals infinity, you can see that the molar concentration, you can see that it's fully diffused together. Now, for the molar diffusivity flux, we can see that H2O is on the top, D2O is on the bottom. You can see it's negative 2.78. We can see it's very steep. Nothing's really happening like all the others at 0.1 second. It's slowly starting to happen, but you can see in its initial stage, it is at a peak. It has a large peak. It's at a large peak, and it hasn't really started to diffuse. And at t equals 60 seconds, you can see that this peak is broadening. You can see it's going to the left, it's going to its left, it's going to the right, and you can see at its final t equals infinity, it fully diffuses. Its diffusive flux, its total molar diffusive flux is equal to 0. You can see that it's fully diffused. 2.78 minus 2.78 is 0. It fully diffused. Now, the mass flux. You can see it also, nothing is occurring in the small segment. It's just starting to diffuse, and we can see negative 5. We calculated this above in the above equation. And we can see that it's starting to slowly diffuse. Its mass flux is starting to slowly widen out. And then at infinity, you can see that it's fully diffused. It's at equilibrium like the rest. Now, thank you for watching. I really appreciate you staying for the rest of the whole video.